Good morning, everybody. This is Todd Barr, the CTO of SolSpec, and this is the first SolSpec Tech Talk. We hope this to be the first in a series, and today we're going to be talking to David Bitner about serverless spatial, serving up COGS in AWS through Lambda functions. Go Dave.
Thank you, Todd, and welcome everybody to this inaugural SolSpec Tech Talk. And as Todd said, we are going to talk a little bit about serverless spatial today and what that means for how we all can serve out our data or do other fun things. So what is serverless? This is one of the big misnomers of the industry. Really, serverless is functions as a service. So it's allowing us to take small bits of code and run them in an incredibly scalable way. There actually is a server, you just don't have to manage it. What serverless brings us is it allows us to not have to worry about any kind of scaling. When we're dealing with these functions as a service, they're actually small bits of code that can spool up in a matter of hundreds of milliseconds to a couple seconds. And we'll talk about some of that difference and what makes that startup time. But they're really designed so that, that scaling up process. So even if you're using things like Kubernetes or, some of these other setups for being able to auto scale, those still take several seconds to several minutes to spool up a new instance. With serverless, the joy is that you don't have to worry about how fast it takes something to spool up, because it'll just spool up however many resources it needs to on demand. And I should mention before we go any further, if anybody has any questions, go ahead and use the chat feature on the webinar. And Todd will be monitoring that chat channel and will kind of key me in to be able to answer any questions you may have. So what are some of the key features that we have when we're talking about serverless functions? The key thing is they need to be small. Serverless is not something that we can use to drive, large data processing, large things. Each unit within a serverless function needs to be pretty small, and I'll talk about what some of those limits are specifically related to Amazon's Lambda in a little bit. Serverless functions are always stateless, so you don't have a data store. You don't have storage system behind it that you can access. You need to also kind of get your data as you go or use things such as databases. Serverless functions are also event-driven. So most of what we're going to talk today is about things being driven through web requests, but serverless functions can also be driven by many other things depending on the serverless platform. There are many serverless platforms out there. Amazon has the Amazon Web Services Lambda. Microsoft has Azure functions. Google has Cloud functions. If you want to roll your own, there's Kubeless running based off of Kubernetes, Apache OpenWhisk, and several others. Through everything else we're going to talk about today, we're really going to put a focus on Amazon Lambda. For no other reason than this happens to be the serverless functions that I personally use. We currently are building on the Amazon stack, and so the choice to use AWS Lambda was really driven by that. A lot of things can be generalized and you can switch between, but unlike some very general purpose things like Docker, these serverless functions tend to be a little bit more vendor locked in. So what is Amazon Lambda? Basically, it's a server running Amazon Linux. And on top of that Amazon Linux, there are bits of code that you can add. Out of the box with Amazon Linux, you get multiple runtimes that you can choose between. There's Python, there's Node, there's Go, there's several others that are provided by Amazon directly. And there are also custom runtimes that you can leverage from external resources. There are also Amazon layers, and these are features that allow to have shareable code and add-ons. We'll actually be using some of these layers or demonstrating some of these layers in the examples that we'll go into at the end of this talk. But layers can be a very easy way to kind of go from that just basically serverless and working on Lambda to truly having a platform for doing serverless spatial. And we'll show, we'll kind of talk about what some of those layers are that we can leverage. So when I was talking about how serverless functions are small, here's what that means specifically when we're dealing with Amazon Lambda. So Lambda functions are limited to 250 megs of code on top of that base Amazon Linux image. And so this is how these serverless functions can spool up so quickly, is you're really only ever talking about up to 250 megabytes of code that it needs to kind of pull over onto a new instance that's, there are many of these Amazon Linux instances that are sitting up. And whenever you're calling an Amazon Linux, a Amazon Lambda function, it's loading up to 250 megabytes of code on top of that base image. AWS Lambda can use up to 3008 megabytes of memory, and they can run for up to 15 minutes. If you are using the API gateway, so if you are using Lambda to serve web requests, that is limited to 30 seconds. The different events that can trigger calling a Lambda function. The big one, and the one that we'll be demonstrating today, is using web requests. And so these are all brokered through, in the Amazon world, the API gateway. But you can also trigger Lambda events off of several other things. You can trigger them off of storage. So if you're using S3 for storage, you can have a trigger that says, hey, somebody added a TIFF or an image with some kind of geospatial image into an S3 bucket. You could have a trigger that runs a Lambda that will convert that image into a cloud optimized geotiff and saves it somewhere else on S3. So you can have various different kind of triggers that you can automatically do some of this data processing without having to set up large chain works or spool up different machines. Again, as long as you can fit within those limits of the Lambda as far as time and memory. You can run Lambda events on a schedule, just like a cron. You can have it so it'll spool up a Lambda function, do whatever processing you need, and then it'll automatically spool down. You can run it from the command line, so you can just call a Lambda with certain arguments from your command line, or interact or wrap it kind of with any other processing you're doing, perhaps on your local machine. You can trigger Lambda functions through your authorization method. So you can, if you're using Amazon's Cognito user pools, when a new user is added, you could run a Lambda function that does updates into a database that has all of your user information. And you can create change pipelines where a Lambda function calls one or several other Lambda functions. I use this a lot if I need to crawl our S3 buckets. I'll have one Lambda function that kind of does the crawling, and then each time it finds a specific type of data file, several other Lambda functions that know how to process that data file. So it's really handy to be able to trigger these Lambda functions through kind of many different methods. And I might take a pause, see if we have any questions where we are right now. Go ahead and throw those in the chat. I'm not seeing anything come through, but want to make sure we take an opportunity to double check in with folks. All right.
Doesn't seem to be any questions.
All right, we'll keep rolling forward then. And please, if you do have questions or things that you want me to clarify or go into, definitely type those into the chat, and Todd will make sure that I catch on to those. So one thing about Lambda functions, especially if you're integrating it in with other services, is it can be really hard to kind of get all the different moving pieces right. So for a web service, you need to have the right permissions on the user that's running the Lambda. You need to have API gateways set up. If you have authorization, you need to have Amazon Cognito. There are several different moving pieces that you need to make to have a lot of these Lambdas work. Serverless.com is a framework that lets you kind of just do all of that in one configuration, and it will configure all the different components. There are a lot of other frameworks out there. Serverless is what I use. My main recommendation is when you are starting out using Amazon Lambda, find something like serverless. It doesn't have to be serverless. There are plenty of other frameworks out there, some that are specific to certain languages. Serverless is agnostic on the language. That's kind of why I like it, but there's some that are very specific to if you're running, say, Python, WSGI functions that work really well. But it can be very handy when you're getting started to have something that's kind of wrapping away some of that, some of those things that can be a little frustrating to get started. Lambda layers. There are several out there that are very useful for getting started with using geospatial data. GeoLambda is one that's put out by Development Seed that provides Google and Rasterio. There is a Poodle Lambda layer that lets you work with point clouds, and Howard Butler has some great examples of being able to call Poodle pipelines directly against LiDAR data that's stored in an S3 bucket on Entwine. That's not one that I worked up into the examples that I'll show later, but is a great thing to play with if you're dealing with serving up LiDAR. Map Serverless is just a basic layer that I will be demonstrating, and that I do have code for demonstrating how to create layers that provides a map server environment that you can use in Lambda. There are links to all of these layers and to all of the examples and to the slide deck for this show. You'll see at the bottom of the screen the github.com Bitner serverless spatial. All the links to kind of find those layers and all the links to all the examples I'm going to show are available at on that GitHub repo. So one trick when you're dealing with Lambda, the way that Lambda works is when the Lambda first starts up, when you first make a request, that's considered a cold request. And what that does is, so we have that Amazon Linux instance, And when you make that request, it needs to pull over that up to 250 megabytes of code that you're using, and it creates any network connections, so any VPC connections, any database connections, and it sets those up. And that's what's called a cold start. So every time it needs to pull up a new instance, so if you make 10 concurrent requests, it'll pull up 10 instances, but then for the follow-on requests, it'll reuse those instances. And an instance can stay up for, I think generally they stay up for about 15 minutes, and then it spools back down if it's not getting used. All of this is happening behind the scenes. You don't have control of it, other than the fact that you can kind of spoof having several requests to keep things warm. But when you have these cold starts, they can take considerably longer than your normal requests to Lambda. So it can be good to try to take activities for things that are just very periodically used and where things aren't going to be kept warm naturally, to try to limit the time that these cold starts take. Couple things that you can do to make those cold starts faster. VPC connections, so setting up networking to other Amazon resources, can be very expensive. Like this can take multiple seconds, which doesn't seem like too much, but when you're trying to respond to a web request, multiple seconds can be pretty painful. If you can avoid those VPC connections, your cold starts will be much faster. Keep your code pack as small as possible. You have 250 megs. Don't use it all if you don't need to. Don't use smaller layers. So when you are using a layer, that counts towards your 250. It's not just what the code in your application. Use the lowest memory setting that you need. This will help with cold starts. But note that your CPU power scales with the memory settings when you are setting up the memory that an instance can take. So, for example, like when you are using the map server Lambda that I'll demonstrate later, because map server is using quite a bit of CPU, you can actually end up getting much faster. Even though it does not use much memory, you can get much faster results if you set a higher memory setting when you're setting up your Lambda. Also, when you're looking at costs, don't just assume because your costs will be lower if you use lower memory, but because of the fact that the CPU scales with your memory, sometimes you can actually end up being cheaper and faster by picking higher memory amounts, because by going with double the memory, it might take half as much time because you also have double the CPU resources. If you are using database connections, make that connection outside of your function. So you'll have code when you start looking at serverless functions. And if you create your database connection outside of that function, the database connection will get made on the cold start, and you won't have to make that connection on each successive function call. So I'll take another pause for any questions. Still looking pretty quiet there.
Yeah, it's pretty vacant.
Pretty vacant. Any of you awake? Somebody just say hi. You're really quiet. All right. We'll keep plugging through. So the first serverless function that I want to demonstrate, and this is something that a lot of people have made comparisons to sort of this newfangled serverless and saying, well, that's just like going back to CGI. And there really are a lot of similarities between using serverless spatial and kind of the way that we used to do a lot of our development using CGI processes. This is a quick example to that wraps a CGI process that just kind of puts a little exclamation point on that matter. And this is actually map server that has been wrapped in serverless. And so we can run the map server C process that just has a little bit of a Python wrapper to make the call to the C process. And now you can see we've got a vector layer, these borders, as well as a geotiff that are being served from map server, all using Amazon Lambda. And just to see a little bit of the performance, let's even kind of pull up our network console. And we can see with pretty conservative memory settings, we're taking about a little over half a second to render each image. But the thing to remember is, even though that's taking half a second, we can throw thousands and thousands of requests at this at the same time, and we never have to worry about any of that scaling. These examples, there are live links to these examples on that GitHub page, as well as links to the actual code that are running these. So these are some great examples if you want to see kind of, hey, what's it take to create a Lambda layer? The map serverless layer demonstrates that Lambda, how we created that layer. If you want to see how to create, how to actually spool that up into Lambda, that's where you can go to this map serverless. Next example, and this is really where I got kind of started out in working with Lambda. And this is based on Vincent Sarago, who I see is online right now. So thank you very much for putting this together. This is what really got my start working with Amazon Lambda. But this is just serving cloud-optimized geotiffs through Rasterio. And it's just making little calls. And this, to me, is one of the greatest use cases for serving, for using Lambda. By storing your data as a cloud-optimized geotiff in S3 and having just this lightweight wrapper, now you have this ability to serve any geotiff, any imagery, any elevation data directly out without having any other infrastructure. Just your data sitting in an S3 bucket or really anywhere web accessible and the function. So the link to Vincent's Lambda Tyler repo can be found on the Serverless Spatial GitHub repo. And it is a very fantastic resource. If you are creating APIs, there's also the Lambda proxy that Vincent has created. And the Lambda proxy gives you a very nice framework for creating different APIs. And he's actually just kicked out a new version in the last week, I think, that even allows for auto-created Swagger docs and some other great features. But this, out of all the examples, is the most directly applicable and useful for anybody who is using geotiffs or serving up imagery or elevation models. I have not published it yet, but you can also kind of build upon this framework and add on-the-fly processing. So internally at SolSpec, we have an application that uses our elevation models and will dynamically create, will Hold on,
Looks like we have some questions.
oh, we have some questions. Okay, we'll dynamically. Oh, just a smiley face from the top. Thank you. But where we can dynamically create hillshades using the Google code, and so there's some fantastic things you can do other than just kind of even directly serving that imagery. I believe that there are some examples of doing some on-the-fly, color correction, histogram stretching, and the like. But this is, if you have one takeaway and you're doing anything with cloud-optimized geotiffs, kind of this should be the biggest place that you start, because it is directly production ready, with very little effort. And moving on to an example, if you need to run a proxy, and this could be a proxy against any service, I've created, and there's a repo that you can run map proxy. So the maps that this is serving are being served off of, I don't remember what service, one of the OpenStreetMap services, but we are just proxying that. And so if I zoom in far enough, it's taking a little bit longer because it hasn't cached those, but it's just using an S3 backed cache, which you could even use a Redis backed cache if you were using Amazon's Elasticache service, that would make it even quicker. But this can be a way to, hey, I need to proxy some services and don't want to worry about, provisioning any of these additional resources. And one more example that I'm going to go point out, vector tiles. So everybody wants to serve vector tiles, and this vector tile server is just a simple little bit of Python that is making a call and using the st as MVT function in PostGIS. Now, I will warn you, if you go to my live examples, while the server, the Lambda function, will scale like crazy, the PostGIS database that I have behind this example is in Amazon micro instance. So if a bunch of you go and hit this example at the same time, that Postgres instance will run out of connections very quickly. But you can see, it very easily scales, and all this is doing, all the work behind this is happening in just a Postgres query. There's several other projects out there doing the same thing. So Tegala, which is the Go-based vector tile server that can key off of a geo package or off of PostGIS database, has some Lambda, has some specialized binary that works well with Lambda. There's some other great work that Azavia has done with some tile servers. So there's a lot out there, and it can be great to just go out there, find some of these data, and all you need to do is create an Amazon account, make sure your credentials are set up in your environment, and these are some great places that you can go and start. Now, I was talking about the limitation here with the vector tile server. Hey, this particular example relies on a database connection. So, you do have to worry about, what scales and how you talk to your data. Remember, our functions themselves are stateless. So you need to pull that data in. Now, in the case of the cloud optimized geotiff, that's a great example where you can have that data in a way that is easily accessible over the network. And it really works great that way. And scales well that way. Some of the vector data sets, if it's a database-backed data set, you really need to be able to scale that database or make sure your database is robust and can handle all the connections as well. Otherwise, you need to have the overhead to be able to pull that data into your local environment. So there's not as clear direction kind of on the vector side of kind of what are those data formats that can really work well with Lambda. If you had an S3 bucket of vector tiles that were already pre-generated and you just wanted to use Lambda to serve those, that would work great. If you have small GeoJSON files that you can kind of copy over and serve up, as vector tiles, or kind of do some transformation on things, that can work well. But kind of working against a large shape file that's over the network, or geo packages that are kind of need to be pulled over kind of into that 250 megabyte limit package, you can run into some more issues. But those are kind of some of the examples that I wanted to go through. And that is that is kind of the content that we have for today.
Okay, let's see if there are any more questions. Silas, there's this thing on.
Any benchmarking? Yeah, so I've done a fair bit of benchmarking, particularly on the, whoa.
Yeah, this is the first time using GoToWebinar, so there's gonna be some bugs.
Give me a second to try to make it so I can see all the questions. I can kind of see one at a time that are coming through. But so onto that here, Todd, can you play with this?
Sure.
While I try to answer onto the benchmarking question. Really, I found that sort of I haven't been able to get below sort of there's always about a 200 millisecond kind of startup when running each function. And oh, this interface is being weird. And as you add on database connections and you get some of that overhead, I found it's pretty darn easy to keep most of these requests, if you set your memory settings high enough, kind of under 500 to 600 milliseconds. And you can get, if you kind of really can limit things down. So if you're just using like the Lambda tiler against a cloud optimized GeoTIFF, and you don't have you're not putting any authentication on with, say, Cognito, you're not making any database connections, that you can get, in the couple hundred milliseconds range. If you put some caching on with using sort of the Amazon's Elasticache. Oh, there we go. Now we can see the questions. You can get things sticking really darn close to that 200 millisecond level. Oh, sadly, we're just seeing a bunch of these pictures that we didn't see before. Sorry for the background noise that we had. Best practices for chaining Lambda functions. I don't know of any best practices. I think that there's, it's going to be, there's lots of tools that'll do the same thing. I found that for some of the things that I've used chaining with, it's worked well just because I can just keep everything in Lambdas. And so I don't need to worry about kind of pulling up a bunch of the different tools. Going back through some of the older questions, Carlos, it is Poodle. Look at the logo. And as the owner of a Poodle, I am very happy by the logo behind Poodle. How do you price this? Lambda can be, to get started and to play with Lambda is dirt cheap. Obviously, if you are fully saturating servers that you have running, the servers that you have running are going to be cheaper. Lambda really shines when you have ephemeral data needs. So it's, if you have needs where, hey, this might spike, at different times, and it might spike hugely because it will scale. It'll scale, I wouldn't say infinitely, but it'll scale beyond any need that I have ever had, without you needing to do anything. A little bit more overhead than if you were running the resources yourself, and it would be more expensive than if you were able to manage your own servers such that you could keep those servers saturated. The nice thing is you just don't have to worry about that at all. Slides are available. The slides are on that link at that link that is at the bottom of the slide that's up here right now. Advantages of map server over GeoServer. I just like map server. The nice thing about map server never dies. Map server is a cockroach. It just, and in this instance, map server, sort of that CGI based model, works really well, translates really well to the Lambda environment, because map server starts up and it dies down, whereas GeoServer, you need to get up and kind of stays up. Serverless with MapNIC. I don't think I've seen anybody doing anything serverless with MapNIC. There probably has been, and I bet if you do a Google search, you'll find that out. I'm going to scroll down a little bit more there, Todd. So somebody else asked about MapNIC.
Silas did it twice.
Oh, Silas did it twice because we're slow to figure out that where the questions were. There's a chat window on here and a questions window. We have the chat window fully expanded, but didn't notice the questions. Cost versus EC2, and that's where I was talking. If you can keep your EC2 instances saturated, your EC2 is going to be way cheaper. So just a benchmark. So I've had these Lambda services running for several months, and have been getting people playing with it off Twitter from my talk that I did at FOSS4G. I am still well within the free tier. The Lambda services we're using at SolSpec, I believe we are still within the free tier. I don't think we've even paid for any of the Lambda yet. So detailed of your vector tile setup with MB tiles already created. Yeah, so Peter, I don't have, so the vector tile server that I made is just running it Postgres tiles on the fly. Tegala, I believe, will kind of has a backing cache to it if you were to use Tegala, T-E-G-O-L-A. I forget if I have a link from that on the, I think I have a link from that on the website as well. All right, so Vincent, 1 million tiles, $5. That's a pretty nice benchmark. Basically, Lambda's cheap.
For the price of one Vente latte.
Yeah. That being said, like anything, you start to scale it, and you start to have the significant resources, it can add up. I think that gets us through all the questions.
Yeah, it does. Okay, well, if no one else has any other questions, we'll go ahead and wrap this up. Thanks for your time, and thanks for attending SolSpec's first Tech Talk. And this will be up as a blog entry and a video later today, along with the relevant links. Thank you very much. Hold it. We got you guys. Resolution.
Resolution, it'll go down to whatever resolution you want to go down. That all depends on your data.
Thanks, Cordelia. Okay. Thanks, everybody.
Thanks, everybody. I look forward to talking to you at our next talk. Bye.
Bye.